Now, what is perturbation theory essentially? Well, it kind of rips a page from the book of calculus of variations. What we're doing is we're taking a potential that we fully understand. And then, since we already know the solution to 100% accuracy, what we're going to do is we're going to make a small perturbation, a little bump. And we're going to denote that as some scaling factor multiplied by the new potential of that little bump, h prime. And so, how do we solve the Schrodinger equation with this new Hamiltonian? What's the new wave function, and what are the new energies going to be? Well, the answer to that involves a power series. What we're going to do is we're going to take psi as a power series of the scaling factor, lambda, along with e. I erased it here, but it's also going to be a power series of the scaling factor, lambda. So what we did here was, once we had both of them written out as a power series, we just plugged back into this equation and set them equal to one another. And so, oh, sorry, not this equation, that equation, and set them equal to one another. And what we got out the other way was these equations. Well, the first equation is nothing special because we just get what we knew at the start. H naught psi naught is equal to E naught psi naught. But then the second one already gives us some new stuff. H naught psi naught plus H prime psi 1 is equal to E naught psi 1 plus E1 psi naught. And so we can remove the scaling factor, which was, in all honesty, there just so we could do this power series trick, and we set them equal to one another. Then we take the dot product of psi naught with these. Recall the dot product is not really the dot product because we're not discussing vectors, it's the inner product. So it's essentially the integral of the product of these two, which also means that orthogonal ones have zero integral, and any wave function will have a dot product with itself of 1. That's why we call it normalized. Normal vectors also have a dot product. So, perturbation theory works, as we can see if we try it with the dreaded infinite square well. If we take the infinite square well and raise the potential by some constant, let's say V naught, then it turns out that the energy we get, the first order approximation, in fact, tells us what we know is the right answer from basic common sense, E naught plus V naught. On the other hand, if we only raise half, like this, then we get E naught plus V naught over 2, which is not correct, as you can probably guess, but it is a valid first order approximation. So as you can see, perturbation